So there's two types of numbers, like I wrote here. You have your real numbers, which is what the computer can understand. Hence, this is the theory behind computation. And then we have complex numbers, which is what the computer cannot understand, I'd like to think. So real numbers have 5 classifications. Namely, you have your natural numbers, whole numbers, integers, rational numbers, irrational numbers, and I think I've listed all of them. So basically with natural numbers, it's numbers that start from 1 up to infinity, or you can say a set of numbers that start from 1 up to infinity and always increment by 1. And I represent it with this and symbol. So this symbol basically represents a set of natural numbers. And then we have the whole numbers, which is a set of numbers that start from 0 up to positive infinity. And I really just highlighted the O and the 0 here, just for you to kind of remember that whole starts from 0 and is basically represented by the same symbol of natural numbers, just with an O or 0 to show that you're starting from 0. They always increment by 1 and are used for computational indexing. If you think of your arrays or your any type of indexing basically, so let's say you're trying to convert binary numbers to decimal, or octal numbers to decimal numbers, or you can say hexadecimal numbers to decimal, you'd basically index starting from 0 and to infinity. So it's used for computational indexing and used for like your number systems counting. For example, you have binary, octal, decimal, and hexadecimal, and are represented using the NO symbol. Integers would be a set of numbers that start from negative infinity up to positive infinity and always increment by 1. And you can say it's an extension of whole numbers to the left or the negative side, because remember, whole numbers start from 0 up to infinity. So if you were to extend that equally to the negative side, you would have up to negative infinity. So it's used really for your int data types. If you would like to declare, I do C++ programming, so you would want to use int to for your integers, and integers can be negative or positive and are represented using this Z symbol. Some textbooks have your Z and then greater than or equal to, you have Z positive like that, or Z negative. I would think with the one that's positive, you're basically stating that you're starting from maybe 1 up to positive infinity, which you would just say it's natural numbers. And then the one with the greater than or equal to, I think it starts from 0 up to infinity, which is like your whole numbers. And the one with the, I think there's a negative one that states that you're going from probably -1 up to negative infinity. So yeah, but I'll just stick to Z as integers, whole numbers, and natural numbers. Then we have rational numbers. So rational numbers are a set of obviously infinitely many numbers, different kinds of numbers. So it can be represented as fractions. You can have decimals that you can neatly write as fractions. For example, if you have 0,5, I think you can write this as 1/2, right? Neatly. And if you have fractions, you would want your numerator and denominator to be both z integers, and where the denominator cannot be equal to 0. If you check this, for example, your numerator is an integer and your denominator is an integer. However, the denominator is not equal to 0. Think this could be written as 1/4, -1/4, like so. So it can also be written as a fraction. They have recurring and terminating decimals, meaning that they're recurring like this, or terminating, meaning there's nothing that comes after this 5. Recurring would mean if you have something like this means you have 0,333 and so on up to infinity. So to show that the 3 is recurring, you would just have a dot. if it's like this, then it means you have 1 comma 1 2 1 2 1 2 1 2 up to infinity. They have perfect squares or cubes. For example, square root of 9, that is equal to 3, I believe. And they are used for your float data types if you think of your C++ and are represented using this Q symbol. Your irrational numbers are basically a set of different kinds of numbers. I forgot, let's say you also have a square root of 2 where you can't really, it's not a perfect square, so you can't really solve further for this. You'd have 1 comma a lot of decimals. So basically it's non-recurring decimals if you check this here. So this decimal is non-recurring and it continues. It also is non-terminating. There's no perfect square or perfect cubed. It cannot be written as a fraction, and you would want to use this as your double data types and are represented with this Q and a naught. So basically, real numbers are a set of your natural numbers, whole numbers, integers, rational numbers, and irrational numbers. And the symbol for real numbers would be this R, like that. Properties of real numbers. So firstly, we have the distributive law, which states that you distribute evenly with corresponding terms. So this 2 is going to be distributed over, like so. And you would have this. This helps you once you do sets. They're going to ask you, or basically to distribute or prove that maybe this is equal to its distributive property. Then you have the commutative law, which states that if you have 2 plus a, this is equal to a plus 2, and it also works for multiplication as well. So with sets, they're going to ask you obviously to prove the commutative law, and you have to know how to do that. Lastly, we have associative law, which also works for multiplication and addition. So if you have things like your groups, what I have on my left hand side is equal to my right hand side. And also for addition, what I have on my left hand side is equal to my right hand side. Just don't forget your oddness. That states deal with the brackets first and then your multiplication if you're dealing with the multiplication associative law, and addition for addition law. And if you have sets, this is how they could ask you to prove that things are associative. So they could say prove that the left hand side is equal to the right hand side, and you do have to know how to do that. Please do check out the video on proofs regarding sets.